We now turn to Kriging. Kriging is a vast topic. In fact, there's a huge literature dealing with all kinds of theoretical and practical aspects of Kriging. Because it came out of mining, there's two different ways of thinking about Kriging. One is very engineering dominated and the other one is more statistically dominated. But both of them have converged, and basically Kriging is spatial prediction, is predicting values for locations for which you do not have observations. And then you can extend that to areas, to volumes, etc. The main idea is that spatial variability, the way that processes vary across space, can be characterized by two major components. One deals with large-scale variation, typically some kind of a trend, but it could be a regression model. And the other one deals with small-scale spatial variations or spatial autocorrelation, and that's typically relegated to the error term. So it's a rationale where you think of a process of consisting of two parts, process with a random variable z that is observed at locations sub s. The one part is the conditional mean, the mu of s, that's the large-scale variation. And the second part is what's left, is the error term, the epsilon at s. So it's a signal noise type of decomposition where the signal captures the large-scale variation and the noise is relegated to what's left. And the fundamental theoretical result, at least from the statistical perspective, is this notion of a best linear unbiased predictor, where the prediction is couched in the context of a generalized least squares estimation for linear regression models. So basically, this is the case where one of the basic assumptions for a linear regression model is not satisfied. And that assumption is that the variance is constant and there is no covariance between the errors at different observations. So of course, if you have spatial autocorrelation, there will be covariance at between the errors at different locations. So the result was published in the Journal of the American Statistical Association in 1962. So this is a really old result due to Arthur Goldberger. And the setup is as shown in the equation. So basically, you think of a set of data on a dependent variable y and explanatory variables in a matrix X. And you do the regression and you get coefficient estimates for the regression coefficients, and we call them here B. Okay. And in this particular case, this is an appropriate estimator that takes into account the covariance structure in the error term. So it's a generalized least squares estimator. So then the problem is, how do we get a predicted value for observations that are not part of the sample data set? And those are observations for which we need to determine y star when we're given x star. So we have observations on the explanatory variables for those unknown locations. And that's a very important concept, because in many instances in the social sciences, we don't have those either. So then this doesn't actually work. This only works if we have some information on the unknown locations. So oftentimes, as a last resort, this is modeled as a trend surface being a polynomial in the, so that's a regression in powers and cross products of the x and y coordinates of the location. So you have the x and y coordinates for every location, so there's no need to get additional variables. Sometimes, especially in environmental science applications, you use information from remotely sensed images to provide the material for the right-hand side, for the explanatory variables. So assuming that we have x star, what is the best prediction for y star? And the major result of Goldberger was that it is not X star beta, which is what you would expect as the traditional conditional expectation predictor, but it can be improved upon in terms of the variance. And the improvement is due to the second term in this equation. And this is a little complicated, but just first focus on the last part. Y minus xb is a vector with all the residuals from the regression. So on average, these residuals are 0. We have all the residuals in the system. This is pre-multiplied by the inverse of the variance-covariance matrix. So you could call this a precision matrix, but it's just inverted, and this is of the same dimension as this vector. So if the vector, say, has 100 observations, the variance C inverse is 100 by 100 matrix. And then this is pre-multiplied by a row vector of covariances between the errors at the new locations, the E stars, and the observed residuals. Now, how do we know this? We don't know the residuals or the errors at the new locations, but we do know how they covary if they covary as a function of distance. And this is where the variogram models come into play. So the variogram models can, for any pair of observations that are a given distance apart, a given h, they can give us what the semi-variogram is, and they can also give us what the covariogram is. So for every pair of observations, we get the distance that separates them, we plug that into the variogram model, and we get an estimate of the covariance. And we can do the same, that gives us the capital C. We can do the same for the unknown locations if we know their distance to the known locations. So for each unknown location, we get its distance to the known locations, and that then gives us the element of the small c vector. And with all those things in hand, we get a new estimate y star, which takes into account not only the large-scale trend, which is part of the x star b, but also the small-scale correlation, which is incorporated in this covariance term, the two covariance terms actually. Okay, so that's the mathematical principle. How does Kriging prediction then actually work? It exploits the covariance as a distance function. As I mentioned, you compute the covariance between the observed points and the predicted point from the covariogram. And so from that, you exploit the structure in the error term, which is reflected in practice by the residual, rather than ignoring that structure. So if there is no structure in the error term, there's nothing to be exploited. But with a non-diagonal variance-covariance term, so there is autocorrelation between the errors and the regression, that is additional structure, and the Kriging prediction actually takes that, exploits that, to get an overall smaller variance of the prediction. That's the ultimate goal. So it's an unbiased prediction because on average it is still, x beta, which is the unbiasedness part, because the error terms and the residuals too average out to 0. So they don't play any role in terms of the unbiasedness, but in terms of the precision, they do play a role. And that's where the B for best comes up. So the best linear unbiased prediction is a prediction that actually takes this covariance into account. A naive prediction doesn't take that into account. And so we can show that overall, this has a smaller variance than the standard approach. And as a side effect, not only do we have predicted values, but we also have an explicit formal expression for the prediction error, which is really useful because then we know immediately the quality of our prediction. And in practice, of course, all this will end up on a map. We'll end up with a map of predicted values and a map of associated prediction error. As I mentioned, this is a very complex area with many technical details, but here's the essence of it. The Kriging predictor takes just the usual conditional mean for the large trend variation, and it focuses on the error model. And the best linear unbiased prediction for a given location is used by exploiting the covariance matrix among all the observed locations, that's the capital C, inverted, and then the covariance between the new locations at S, or the new location, I should say, at S, and all the observed locations. That's this row vector C transpose S. So there's a row vector times a column vector, and the result is a single number, if you're familiar with matrix notation. So basically, if you're not, just think of it as exploiting the fact that there is a structure in the covariation between pairs of locations, and that structure depends on the distance that separates them, and we have formalized that structure in a variogram model that has parameters. So we just plug in the distance, and given the parameters, we have a value for that covariation, and that then allows us to make the prediction. And by the same token, the prediction variance, here's where you see how it improves upon the standard process. The standard prediction has as its variance, so the sigma square of the prediction is the sigma square, the variance of the process. But when we take the covariance into account, we subtract an element that is actually positive, and that element is this product of a row vector, a matrix, and a column vector, and such a product is a single number. So we see that by exploiting the covariance, we improve on the precision of the prediction. Now, of course, if the covariance is very small, the improvement will be very small. And we already know that as two observations are further apart from each other, the covariance will be smaller. So for observations that are very far apart, the improvement from this approach in terms of prediction variance will be minimal to negligible, which is something we will exploit in practice. But for short distances, the improvement can be quite considerable. Okay, then in terms of a taxonomy of Kriging models, the classification really has to do not so much with the error term, because that's always the same thing, but with the way in which we model or think about the large-scale variation. And there are three broad categories. There's many other ones as well for particular kinds of variables, for example, for count variables or for binary variables. This is just a discussion in the context of continuous dependent variables. So simple Kriging is basically not useful. Ordinary Kriging is sometimes used. The mainstay is universal Kriging, or as it's also called, Kriging with external drift, KED. So let's go through all three of them very quickly, and then we'll get a sense of the differences between them. So simple Kriging assumes that there basically is no large-scale variation. So the mean is constant. Not only is it constant, it's assumed to be known, so it doesn't need to be estimated. So this is a model to illustrate the technique. It's a typical textbook model, but it's not a realistic model because there is no realistic context where you would actually know what this mean is. So simple Kriging is good for reference and maybe to work out the math, but it's not very practical. Then the next step up in terms of complexity is ordinary Kriging. And ordinary Kriging still has a constant mean, but now we don't know what it is. It needs to be estimated. And so the Kriging exercise then has to do with predictions of deviations from an unknown mean. So the mean is constant throughout, and then we take deviations from that. And remember, when we started talking about the geostatistical perspective, one of our assumptions was moment stationarity. One of the requirements was moment stationarity. And one of the moments that had to be stationary, meaning constant, was the mean. And so this satisfies that requirement in a strict sense. But in practice, the mean is typically not constant. There are trends in the data and another variability. The mean, in fact, varies with location. And so how do we get back to this moment condition? As we discussed previously, we look at the residuals of a regression model. So universal Kriging or Kriging with external drift is really a model that focuses on the covariance among the error terms of a regression model using the residuals in the prediction effort. So the model then is z at location s is a linear function of variables x observed at s with a parameter vector b and the error term. And as I mentioned, there's many extensions for different types of models, for different types of dependent variables, and there are many technical issues as well. One issue that I haven't covered here is what is this prediction for? And there is a whole range of technical issues and a variety going from point-to-point prediction, whereas you have a model estimated for points and you predict points. This is the exercise that we'll carry out in the lab. But you can also go from point to areal prediction. This is called block Kriging, or even volumes, for example, in many mining applications. The volume is really what one is interested in. And then there's even a literature on area-to-area interpolation of area-to-point interpolation. So there's many technical issues that we don't really have the time or the scope to cover in this class. What we're going to do in the lab, primarily, what you're going to be doing in the lab, is to apply this by going through the exercise of looking at the data, estimating an empirical variogram, identifying a proper model for the variogram, estimating the parameters, and then using the parameters to make predictions. So how do you actually do this? Is the prediction is from point to point. So we typically put a fine grid of points over the original observations and then estimate or grids, very fine grids over the original observations, and then produce an estimate for the midpoint of those grids. And if those grid cells are small enough, you can color them by the value of the prediction, and then it looks almost like a continuous map. So it looks almost like you've predicted for any location on the map. And the counterpart of the prediction, as we saw, is an estimate of the variance or the standard error of the prediction. And the two are related to the distance from the reference points. And as you can imagine, as you get further and further away from the reference points, there is less and less covariation. So there is less and less use of the whole creaking rationale, and the prediction error will start approaching the variance of the process, and so there will be very little gain of using the creaking mechanism. So in a nutshell, creaking is very good in predicting close to the observation points. It's not so good at predicting as you move away from the reference set of the observations of the support, so to speak, in statistical terms. And to close this discussion, I will show you some illustrations of predicted value maps. For example, for the Baltimore house price model, when we take the second order trend surface and we predict the values, and then we add in the creaking model for using the residuals, and we predict this for a very fine grid overlaying the data. If you look very carefully at the slide, you can actually see the little squares or the shape of the squares, and then we use a gradation, from low to high. And as we already know, there is a spatial trend in the house prices in this Baltimore example, and the brighter, lighter colors are in the north and in the west of the city, also corresponding to the larger circles. Then matching this, as I mentioned, is a map for the prediction standard error, which we see gets worse, more pink, as we move away from the points. And similarly, for the exponential model, we can show a predicted values map, and the maps, if we go back, they're very similar. They have the same general shape, but there are some marginal differences when you look at them very carefully. And the predicted standard errors map has a very similar shape. So basically, now we have all the tools to do spatial prediction. We start with the empirical variogram, fit the model, get the parameters, use the parameters to make predictions over a fine grid over the data. And next, I'll close with some practical issues to keep in mind when applying this in a real setting.